Hello. Last lecture was an introduction to our ML systems course. We had a glimpse of the challenges with modern large scale machine learning models, be it during training or during serving. Today, we are going to actually dive into the course and look at an important component of all modern machine learning frameworks, that is, automatic differentiation. In today's lecture, we are going to have a brief look at a typical modern deep learning stack, followed by a quick recap of some essential concepts from deep learning and gradient descent to see where automatic differentiation fits in and the problem it helps us solve. We'll discuss the details of the AD algorithm, specifically the reverse mode variant of it, which is widely used in machine learning. We'll discuss some of the challenges which arise when implementing AD in practice and a very quick look at the sort of optimizations proposed to deal with those challenges. We'll have much more to say on these optimizations when we discuss optimization and computational graphs later in our course. We'll end with discussion of how backprop is implemented in actual Python code by looking at the Needle library, which is an educational framework proposed by CMU. Machine learning frameworks expose user friendly abstractions where we specify the architecture of a model and the type of data and where it's coming from, the source, and the specifications of the optimization algorithm to use. These easy interfaces mean that the code we write isn't that much in volume, a few hundred lines, and it doesn't take very long for us to write this and specify this. Underneath, the systems part is really the software machinery, which does a lot of heavy lifting. It also interacts with the hardware to make sure that our heavy computation runs efficiently on these devices without issues. In the early days of deep learning, when the system stack wasn't very mature, researchers had to write quite a lot of Python code and also low level code such as CUDA kernels. But these days, the system stack is more complex and has several components, but they are all integrated into and managed by the machine learning framework like PyTorch or JAX. Here are the components of a typical deep learning stack at different levels of abstraction. So we have the user interface which we actually use when specifying our model data sources in PyTorch. So this is part of the user API. And we are also including automatic differentiation here because we do use, we interact with the AD engine via things like loss dot backward or seeing this tensor requires gradient and finally accessing the gradient using dot grad. But really, maybe the automatic differentiation engine should come within the system components where the details of how the competition is going is really hidden from us. The systems component also includes the part which does optimization on the computation graph and the kind of transformations which are applied. So these would probably we would call under the name of machine learning compilers. The runtime environment, which PyTorch includes, that takes care of runtime and parallel scheduling. One level beneath that are the libraries which do computations like matrix multiplication or convolution efficiently on the GPU. Now, these aren't really so much part of the ML framework like PyTorch, but PyTorch does interact with it and manage it in a way. This part includes things like cuDNN and cuPlus from NVIDIA when working with NVIDIA GPUs. And accelerators and hardware backends, those are another component which are quite low level, probably we won't have much to say about it right now. And in today's lecture, we are going to focus more on automatic differentiation and really what goes underneath the hood for that. Thinking of classification problem and machine learning, we typically transform the input to a feature vector over which we apply a linear classifier to obtain the class. In this case, we are looking at binary classification. So we apply the logistic function to this code. The loss is an indication of how far our predictions are from the ground truth in the training dataset. It also incorporates a regularization term for better generalization. Note how the loss decomposes as the sum of losses over individual samples. We'll exploit this property later in the course when thinking about parallelism of training over multiple GPUs. We are interested in the set of assignment to the parameters of the model so as to make this loss small. The loss is non-convex, and a gradient descent based approach is dominantly used to iteratively update the parameters. So here we have the vanilla gradient descent without momentum, without adaptive step size. And the question really becomes, how do we obtain this gradient of the loss with respect to the parameters of the model? The part of the machine learning model which brings us from input to the feature vector, we call this part feature extractor. In neural networks, the form of this feature extractor is like a sequence of layers one after another. Each layer can be either matrix multiplication followed by a nonlinearity, or it might be convolution followed by pooling, or attention followed by multilayer perceptron, depending on the kind of input output we are looking at and the kind of model we want to work with. But the key aspect of modern networks is this composition of building blocks. And then we have a classifier on top. Typically, when thinking of training, we are interested in obtaining a good set of parameters for both the feature extractor and the classifier jointly by end-to-end training. So consider a simple two-layer MLP. Each layer is matrix multiplication followed by a nonlinearity. So in this case, the set of parameters are include W1, W2, and WC. So in the previous slide, when we said theta, we mean all the parameters of the model and they are distributed across the layers. Let's take a closer look at the iterative update of parameters. We are interested in the value of the gradient of the loss with respect to theta at the current value of theta. In stochastic gradient descent, we approximate this quantity by an average of gradients computed over the individual samples in my mini batch. Using mini batch instead of the whole training set accelerates training due to computation efficiency. It helps us deal with constraints of the GPU memory, and also it leads to sometimes better optimization due to noisy gradients. One could formulate these gradient computation in terms of equations, and it's certainly more feasible for the two-layer MLP, which we saw in the last slide. But for complex large-scale modern neural networks, it's very tedious to implement this by hand, and it's also error-prone. The large number of parameters means that the sequence of operations is quite heavy, it's quite large, and our gradient function implementation may be inefficient unless we take special care. And that is why we make use of automatic differentiation, which is an algorithm to compute gradients for us automatically. So autodiff is a general algorithm which takes in an input, a function, so let's say a Python function, which given an input, the function returns a value. So autodiff takes in as input that function and returns another function. And this gradient function we can query at any value to obtain the gradient of the input function at a particular point. So AutoGrad really or AutoDiff, it looks at the sequence of operations happening in our procedure and captures that information in a data structure, which we call a computational graph, and applies a particular algorithm on that data structure. This way of stating AutoDiff as an algorithm which takes in an input of function and returns a function, that's the classical notion of automatic differentiation. But the interface which we use in Python, it looks a bit different than this, but the core idea still remains essentially the same. There are two modes of automatic differentiation, and here we are going to focus on the reverse mode because that is the one most dominantly used in machine learning. So a function let's say it takes in the input which is a multidimensional vector and returns a multidimensional vector as output. So that's in the general case. In the special case of neural networks, the output which we are looking at, so for instance, if I go back, L, it takes in an input, a multidimensional vector. So let's flatten parameters in a huge vector. And the loss is a scalar. So in the special case, when the output of the function is a scalar, which occurs in machine learning, when we apply the reverse mode AD to the special case, it is what's called backpropagation algorithm. AutoGrad is the name of a particular automatic differentiation package, but modern ML frameworks like PyTorch, TensorFlow, they have their own Autodiff engines built in within them. Automatic differentiation is not finite differences, it's different from that. So the method of finite differences that would give us an approximation of the gradient. And in the case when we have a huge number of parameters, it's also very inefficient. Whereas Autodiff is much more efficient and also numerically stable. So that's a huge win over the method of finite differences. Automatic differentiation is also different from symbolic differentiation. So in symbolic differentiation, we specify a function as a mathematical formula, and the output which we get from differentiation is also a mathematical formula. Whereas for automatic differentiation, the input is really the implementation of something as a function, as a program. And the output also is a program, as a program function, really. And we can query that function, we can pass in to this output function any particular theta, and it will give us the derivative of the loss at that particular theta. So it's more general, maybe, yeah, in a way, than symbolic differentiation. Now, the input function that can have things like loops, conditionals, and so on. So it's quite general. Let's do a brief recap of gradients because it's going to help us discuss some concepts that will be useful later. So here we have x and fx, and the derivative of fx at a particular point x naught is really a linearization of the function at that point. So let's think of scalar input and scalar output. We can write this linear approximation as fx naught plus the value of f dash x at x equals to x naught times delta x. So delta x really is x minus x naught. Now, because input is scalar, so delta x is scalar, and the output is scalar, which means that the value of f dash x at x naught is also a scalar quantity. On the other hand, if the input were to be a vector and the output a scalar, which is the case for us in machine learning, then the linearization would look like this. So this term now is grad. grad of fx evaluated at x naught. So we take the transpose, making it a row vector. Delta x is a column vector. So the output which we get finally is a scalar, which is the output of fx. So in this case, del fx is really a vector. In a more general case, where the input is a vector and output is another vector, so let's say the input is n-dimensional and output is m-dimensional, the linearization is now represented by this, where this quantity is now a matrix, delta x still remains a vector. So we multiply a matrix and a vector to finally obtain a vector of dimension n. This quantity, this matrix, is called the Jacobian matrix, and it has shape n by n. Now, let's look at how the chain rule comes into the picture. Consider the composition of two functions. So, x and y both are scalar here. We apply the function f1 to x, followed by the function f2. And we can represent it in the form of a data flow graph as like this. But then the notation which I'm using is that the node will represent the value of an intermediate computation, and the edge will denote what was the operation which led to that value. So for instance, I have the input x, I, I apply the function f1 to it to obtain f1x, and I denote it by an intermediate value v1. I apply f2 to v1 to obtain v2, which is really a dummy variable for the output y. So I multiply this with 1. We do this, we usually have this dummy variable because it helps makes things cleaner for us. What I'm interested in is what is the derivative of the output with respect to input. So dy by dx. I'm going to use a notation called, I'm going to represent the derivative of the output y with respect to an intermediate value, let's say v1, by v1 bar. And it's v1 bar is called the adjoint variable. It's an adjoint of v1. So v1 bar, we can write down because of the chain rule as derivative of y with respect to v2, followed by the derivative of v2 with respect to v1. This quantity, based on the notation which we adopted, we can write as v2 bar. And this is the derivative of v2 with respect to v1. Now, in this case, v2 bar is simply 1. And if we go one step back, I'm interested in x bar, the derivative of the output with respect to x. And I can decompose it by chain rule in this way. Now, these two taken together, derivative of loss with respect to v2, followed by derivative of v2 with respect to v1, is exactly v1 bar, which I wrote here. And then, so we have x bar, adjoint of x is adjoint of v times derivative of v1 with respect to x. Now, in our discussion, we will informally refer to v1 bar as upstream gradient, and we'll refer to del v1 by del x, or even del v2 by del v1 as local derivative. So yeah, so the adjoint of something, adjoint of a quantity, is really the adjoint of its child in the graph times the local derivative. And the adjoint of the child is what you are going to call upstream gradient, because it has been coming by this procedure where we start from the back and bring it back and back. Upstream gradient. For a more general case, when we have this nature of data flow, so we apply f1 to x, resulting in v1. We take v1, and then on the one hand, we apply f2 to v1, resulting in v2, and then f3 to v1, resulting in v3, and add them up to get this expression. So this graph is no longer the neat chain which we saw earlier. And in this case, one can show by means of multivariate calculus that V1 bar is really the contribution coming from this branch and this branch. So we add them up. So the contribution coming from this branch is the adjoint of the child, upstream gradient times the local partial derivatives, and same for this branch. The adjoint of V3, the upstream gradient here, times the local partial derivative of V3 with respect to V1. So when you have this sort of branching, you always add them up. And for a more general case, we can say that this should really be the adjoint of Vj. So it should be Vj bar here. And this is equals to sum or all the children of Vj in my competition graph. And for each of them, I calculate this contribution where it's the adjoint of Vi times the local derivative of Vi with respect to Vj. So we add them all up. And this sets a key equation for us in backpropagation. It's also sometimes called the backprop equation. So here we would say that V2 bar, if you were to look, so the quantity here which we have, maybe let's look at it. That's V4 bar is 1 because it's a dummy variable. So we should have 1 here times the local partial derivative of V4 with respect to V2. And even this quantity is 1 because it's a summation. So a few examples. If, let's say, I take X and multiply it by a matrix to obtain a vector V, so both X and V are vectors, in that case, the adjoint of X, it can be shown that it is W transpose times the adjoint of V. And here the Jacobian is, it turns out to be, it is W. And we can write X bar as adjoint of X as transpose of the Jacobian times V bar. And this is holds generally that we can write the adjoint of a particular node as transpose of the Jacobian times the child node of the in the parent graph, in the competition graph. Let's look at another example where we are doing element-wise exponentiation. So I apply exponent to each element of x resulting in a vector v. In this case, the Jacobian looks like this. It's a diagonal matrix because this is element-wise operation. And here, the adjoint of x is, it will turn out to be, if you were to do transpose of the Jacobian times v bar adjoint of v, it's basically doing an element-wise multiplication of this vector, exponentiation over x, which is really v, with adjoint of v. So this is important because this example is quite good because what shows here is that we don't really form this G matrix explicitly. Rather, we do the computation of J transpose times V bar implicitly in a simpler way, because the challenge really here is when our vectors are have huge dimension, that these matrices they can become quite big. And if we had to form these matrices and then multiply them with a vector, that would make things quite slow and it would take up a lot of memory. Instead, if we could just do things like this, where we do element-wise multiplication of two vectors, which take much less memory, then it's much more feasible. And this is a common thing which we are going to see that in the backdrop algorithm, we'll often have to multiply a matrix with a vector. And we don't really always materialize this huge matrix and then do the multiplication. Rather, for specific cases, it's easier to do it in an alternate way implicitly, which is much more efficient. So let's return to our case. where the loss function takes in an n-dimensional parameter and returns a scalar. And we can write the loss as a function of theta as a composition of these functions. We give the input x and parameter to the first layer, we take its output, pass on to the next layer. Fl is the final layer, and we take its output and give it to the loss function, which returns a scalar value for us. So in this case, what we are interested in is the partial derivative of loss with respect to theta. And in supervised training, typically we aren't interested in the derivative of loss with respect to x. So this is the quantity which we are interested in. Now, now we can write the derivative of loss with respect to theta using the chain rule in this way. So the first quantity is this should really be capital N, derivative of partial derivative of capital N. We use this notation where by theta, I see all the parameters. The output of the first layer I denote by Z1, output of the second layer by Z2, and so on. Output of the final layer by ZL, and then the scalar loss by small l. So derivative of loss with respect to the output of the final layer. So note the loss is scalar. The input here is a vector. So this quantity del L by del ZL, that is a vector. And here we take the transpose of that, resulting in a row vector. All of these other quantities, they represent the previous layers of the neural networks, and each layer takes in a multidimensional input, returning a multidimensional vector, and returning multidimensional vector. So all of these are matrices, all of these are Jacobians. If you wanted to see where this comes from, maybe it might be easier if you take the transpose of this whole thing. So recall this here. We saw X bar was Jacobian transpose times B bar. And then if you take it back and back, then you would be multiply here with the result of this with Jacobian transpose of what comes before and so on. So you can, if you did the transpose of this thing, you would see that here we have a vector and followed by a lot of Jacobian transposes here, but it's more common to write the whole thing in the transpose form. And that is what we have here. See, here we have a row vector, and these are the Jacobian matrices. So let's say that we multiply these two things together. The result of this computation is a row vector, and so on and so forth. So if we carry on this computation from left to right, we will end up with a row vector, which is the transpose of derivative of loss with respect to theta. Here, I'm adopting the notation that the gradient is a column vector, and that is why we are writing it in this way. Sometimes you might see the gradient being represented as a row vector, but it's just a matter of notation. So the question really is, I have to compute this quantity. What is the order in which I multiply these things? Because that makes a lot of difference. In reverse mode backpropagation, we go from left to right. You multiply first the vector and the matrix, resulting in a row vector, and so on and so on. So every time we are multiplying a row vector and a Jacobian matrix. And well, we could have gone the other way to go from right to left. That would have resulted in what's called the forward mode backpropagation. The issue there is that we would be multiplying two large matrices. So we would have to form these. Well, when multiplying a row vector with a Jacobian, just like the case we saw here, we oftentimes don't have to form this matrix and then do explicitly like multiply this with a vector. Rather, we can do it much more efficiently using some way or the other for different kind of operations. So the vector matrix multiplication, what's called the vector Jacobian product, we can do it implicitly, efficiently. But if we choose the other route and try to multiply Jacobians together, first of all, that would take up a lot of time in memory. And so that's the issue. Like for manifesting all these big matrices in memory, it's a huge challenge. Normally, in forward mode, we actually multiply this right-hand side at the end with a vector, which gives us the directional derivative of loss with respect to theta with respect to one parameter. So in that case, we are really multiplying a vector and a matrix. But for that to make sense, the vector has to have one in the particular coordinate with respect to which we are taking the loss, and the rest should be zeros. In that case, we can do a sequence of matrix vector multiplication, which implicitly that can also be done quite fast. But that means that we would have to repeat this process again and again for all these different seed vectors, where the one is in every time in a different coordinate, which represents a different parameter. So you would have to repeat this process a lot of times, probably millions of times for large models, and that wouldn't work. So for the very special case of our networks where the loss is a scalar, the input is the size of the parameter vector is huge. This works quite well because we start off with this, and every time we multiply a vector and a Jacobian, and finally we have the derivative of the loss with respect to all the parameters in one backward sweep. The simple idea of a model being a linear stack of layers, like we saw earlier, is it doesn't really capture the complexity of modern networks. Think, for example, about residual connections. A better model to think about this is what's called a computational graph. So this represents the data flow as a directed acyclic graph. And this graph structure allows for much more complex and powerful data flows, which is exactly what we see in models like transformers. Modern networks, they involve things like pooling, convolution, batch node, dropout, attention. So how do we deal with that? Now, all of these components, they are designed to be fully differentiable. And this means that their contribution to the overall gradient can be calculated and can be propagated efficiently by the backprop algorithm, which we looked at. Let's take an example to see how a competition graph is formed and how do we do a backward pass on this. So given two inputs, x1 and x2, we are interested in obtaining y using this expression. I can represent this competition by means of this computational graph where I first multiply x1 and x2 to obtain an intermediate quantity called v1. Now, on v1, on the one hand, I apply exponent, and on the other hand, it's just like an identity multiplied by 1. And finally, I add these things up together to obtain y, to obtain my output. We call this a computation graph because here the operations, they have been broken down into primitives, into very simple operations. I will add a nuance to it later on, but for now, maybe we can keep it here. So we are interested in what is the derivative of y at x1 equals to 2 and x2 is equals to 3. We could easily do it by hand for this case. Let's see how the algorithm works for this. And for that, we have to go into phases. So first we have to take these values of x1 and x2 and run the computation forward to obtain the value of y. And once we have this, then I'll run the computation in backwards in a way to obtain the derivative of y with respect to x1 and with respect to x2. So obtaining y, given x1 and x2, obtaining y, like the sequence which you have, it's called having a forward trace. So I get v1 as this, v2 as exponentiation of 6, v3, which is my output, so it's multiplied by 1 here, as y. For the backward pass, we start from v3. The adjoint of v3 is 1 because it's a dummy variable. We obtain by multiplying v3 by 1. The adjoint of v2 is the adjoint of v3 multiplied by the local derivative. And because v3 is the sum of these two quantities, we end up with 1. The adjoint of v1 is the sum coming from these two branches. Let's look at the contribution coming from v3. So this contribution in v3 bar times the local partial derivative, and this is 1 because v3 bar so it's 1, and here we have a sum. The contribution coming from here is v2 bar times the local derivative, and this, the operation being exponentiation, we end up with this we end up being v2 bar times v2, and v2 bar we just computed as 1. So this term is, in this case, v2, which is exponent of v1, and in this case it's the exponent of 6. So the value stored in v1. x1 bar, here we have multiplication, so it's adjoint of v1 times x2, and similarly for x2 bar. Now note here in the backward pass, we needed v2, and we also need the values of the inputs. Of course, we could, in this simple case, compute v2 again. But let's say if this graph was quite big and we obtained v2 in the forward pass by doing a lot of expensive operations, we wouldn't want to recompute that in the backward pass. So it makes sense to save these intermediate values so that we use it during backward pass when required. It's more common to actually have a separate computation graph for this backward pass. So let me go. Yeah. So here we add another component to the original computation graph. So the red part represents the backward path. So here's our original graph, and this, in this case it's called a primal graph. And the new part which we added in red, representing the backward computation, that is called an adjoint graph because the nodes here, these are the adjoint variables. Taken together, the primary and the adjoint graph, they are linked, and the whole thing is called, it's a unified graph. Let's see how we obtain the adjoint graph. And for this, it helps to look again at the backward trace which we did. V3 bar is 1 because it's a dummy variable. V2 bar is, it ends up being V3 bar because the local partial derivative in case of sum here is 1. And V1 bar, here it's the sum of these, the contributions coming from here and here. And we represent each of these contributions by separate auxiliary variables. So the contribution coming from V3, we denote by adjoint of V1 dash. And the contribution coming from here, we denote by adjoint of V1 double dash. And V1 dash, it's because of the summation, it ends up being just V3 bar, adjoint of V3. And because it's an exponent operator, this part ends up being product of V2 bar times V2. As similarly, as we saw in the last slide, adjoint of x1 and x2, it's the respective input x2 multiplied by v1 bar and x1 multiplied by v1 bar. And that's how we obtain this adjoint graph, because we can look at, for instance, v2 bar, that's basically v3 bar times 1. So by ID, we mean multiplication by 1. And adjoint of v1, it's summation of the adjoints of v1 dash and v1 double dash. And these quantities themselves, they are, v1 dash is basically v3 bar, so identity on that. And v1 double dash is product of adjoint of v2 times v2. So this helps us link with so there's this dependency here from the primal graph, and that's why we see this edge here. Similar kind of dependency is for adjoint of x1 and x2 because x1 is product of x2 times v1 bar. So it's product of x2 and v1 bar and so on. Now these things, these circled in yellow, these are the quantities which link up primal and the adjoint graph. These are basically the data dependencies. And so instead of saving all the activations, we can just look at those quantities which are going to be used in the backward pass, which the data dependency, these edges tell us, and feed them for the backward pass. Now, one thing to note is when does this adjoint graph get formed? And this happens when we call, for example, y dot backward. When that happens, this backward trace is run. And when this is running, dynamically, the system kind of forms this adjoint graph. It looks at these operations it has to do and it forms this adjoint graph. Typically, we run the same computation again and again, the same thing for different values of x1 and x2. So the same graph usually holds both for primary and for adjoint. So once we have done one pass on that, for another value, we can reuse them. And this also, what's the benefit of forming this separate adjoint graph explicitly? There are quite a few. First of all, if you wanted to take the derivative of derivatives, so if you were interested in Hessians, it's much harder to do it via this approach where we do just the backward pass on this. It's once we have this adjoint graph, we can form another adjoint graph based on this if we were in need of Hessians, the double derivatives at any point of time. Besides, once we have the backward pass explicitly as a separate computation graph, it's much easier to apply optimizations on this graph to speed up operations. So we'll talk more about optimizations later on, but these optimizations, they sometimes take the form of, oh, I have to do this operation followed by this operation. So instead of maybe, can I fuse them together and do them on one go so that I don't have to move things around a lot in memory? And these kind of optimization decisions, they are much easier to make when the graph is explicitly laid out for the backward pass. And well, the final advantage is that this graph tells us which values from the forward pass am I going to need in the backward pass explicitly by means of the dependencies. Even when we know that we only need to save a subset of these intermediate values, even that is quite challenging for large scale models. This graph is from this paper given below. And let's look at the first case for a 22 billion parameter transformer model. And what this shows is that if one were to save all the parameters and the optimizer state along with all the needed activations, then it wouldn't fit in a 100 GPU with 80 GB of memory. On the other hand, to deal with this issue, what one can do is one can be more selective about the activations to save. And in this case, we end up fitting things on the GPU, but this does come at an expense of more computation. This leads us to this idea called gradient checkpointing, which is quite commonly used. And the idea there, so for instance, this here we are considering the transformer model as a stack of MLPs, basically. And each MLP is a matrix multiplication followed by a nonlinearity followed by another matrix multiplication. I'm not showing the dropout here. And the matrix multiplication here, it so if the dimension of this one, the input vector was h, then this matrix multiplication expands it to 4h. So that's the commonly used convention. Now, the idea is that if we were to see all the activations for later use in the backward pass, we would be storing all this, the input here, the intermediate value here, all of these. But because all of this couldn't fit into the GPU memory, I can look at the set of all of these activations and ask myself which of the activations are taking up a lot of space in memory and which are not so hard to recompute. And for that, we can divide up the model into segments and we can save only the inputs going into that segment. So here's MLP, the first MLP. We save only the input going into that MLP. And then we save only the input going to the second MLP and the output of that. Now, if on the backward pass we needed this activation, we could recompute this using this input, the blue one. And if I needed this activation in the backward pass, I could recompute it by doing matrix multiplication on the green saved activation. And this is called gradient checkpointing, although we are saving really checkpointing the activation because the idea is that we are doing this during gradient computation. So checkpointing happening during gradient computation. Let's see the amount of benefit which you get for this. So assume that the pass size is B. The length of the sequence is denoted by S and the hidden dimension is denoted by H. And we are storing each number as, let's say, B float 16, which takes up 2 bytes. If I was storing all these activations, then let's see how much bytes I would need for that. So I would need, in the input, I would have B times S times H numbers, and for each, I need 2 bytes. And for this intermediate activation, because the dense layer is expanding that vector, input vector 2, from H to 4H, we would need 8 times B times S BSH bytes for this. And similarly, 8 BSH bytes for this. So overall, it's 18 B times S times H bytes. Whereas if we were only saving the input, then we would need 2 times B times SH. So we are saving about 80%, around 80% in memory when considering this. Of course, we would have to pay price in recomputing these intermediate activations during backward pass. And we can normally, as a thumb rule, we can expect the training to take about 20 to 30% more time when doing gradient checkpointing. We'll have much more to say about this later on during our discussion of graph optimization, where we will take interest in the question of which are the activations specifically which we should save so that I don't have to do a lot of recomputation during the backward pass.